the last two are just dealing with the inverse power, which is basically saying, remember, E and ln, they reduce each other out. We did have a property in pre-calculus that said if you have the exponent, it'll come down in front, but I don't like to think of it that way. I like to think of it as, you know what? The natural log and base E are going to reduce each other out. So what's left over is x squared equals x squared. That's the inverse property right there. And same thing here is, what if we just flip the order? What if I did the natural log of E? Well, in pre-calculus, we had a property that said this exponent can really come down in front, and then you're left with the natural log of E, which reduces each other out. Another way to think of that is just saying the natural log and the E reduce each other out. What's left over is x squared equals x squared. So this is really kind of a trick just to review some properties for what we're looking at. We don't have any videos to show today. Nothing special with us being second hour in class. We don't have anything too crazy going on. Just make sure that those of you that are in Tartan, we know the correct way to walk around the building. You probably saw those videos yesterday in class, so I'm not going to go over it. I think you guys have it down already. And then we're going to look at some things that gotta love new technology. There we go. We're going to do a quick recall from Algebra 1 and Algebra 2. And this part here, I don't want you to write down. If you feel like, oh man, I probably want to look back at this, these notes will be posted so you can get them if you need to. But in Algebra 1 and Algebra 2, we had something called variation. And what variation was is we have two methods. We have a direct variation and we have the inverse variation. Well, the direct variation was just kind of simply put, y equals x times y. Y equals, how about we do it this way? Y equals x. However, if they're not exactly the same, if they're directly proportional, that means they only differ by a multiplying factor. So hopefully you guys remember seeing this and thinking of this as your direct variation. Here's the mathematical way to state this. Y varies directly with x, or another way is y is directly proportional to x. And they have that written right down here. And remember, we can write f of x instead of y. But all this means to me is multiplication. When you see the word directly or proportionally, it's just multiplying k, which is a constant, times x. And I know this probably doesn't make a ton of sense unless you have a very strong recall from Algebra 1 and Algebra 2. This k value is just a constant. It's something we multiply by. Now, what's an example of this? The linear function y equals 3 times x. X and y are related, and the only way they make a difference is x, whatever x is, y is 3 times greater than that. That's how that relates proportionally. So that's what we're getting to when we say direct variation. The other variation is inverse variation. And we would read this as y varies inversely with x, or y is inversely proportional to x. And the inverse side looks like this. It's divide. So instead of multiply, k times x, it's k divided by x. And that gives us a different type of relationship that we can see with functionality, and that's what we have right here. So nothing super crazy on that. If you wanted to write any of this down, here's kind of the key takeaways just from what we talked about and what we're going to be talking about. We're going to throw this idea of a rate in here today. And you got to remember, when we use the word rate, rate stands for derivative. Now, We could be comparing multiple things, but a lot of times it's just dy dx, right? The derivative of y with respect to x. Or sometimes it's dealing with the change in position over time, miles per hour. That's our rate. But it really just means derivative. And then when you see the words directly proportional, I want you to think multiply. And that's what I just had written up there was directly proportional was just being k times x, and that's it. And then the inversely proportional, when you see that, that was the divide. So k divided by x. And you'll see why this is important and how it relates to calculus, because technically this is stuff you talked about in Algebra 1, and my guess is you probably talked about it for a day. Okay. So how do we use this information? And I don't want you to be intimidated by this yet, or you shouldn't be at all, but it is intimidating to start. Don't write this, because what I want to do is just show you how they want us to interpret this piece of information. Okay, they're going to give us a sentence, or in this case a paragraph, and we have to interpret it and write the differential equation. And that's how this ties into what we're learning today. So let's read through it. Again, I don't want you to write these first couple pieces. I just want you to see how it's set up. So Catherine runs around a linear path. Her position is given by the function p of t, where t is measured in seconds since she started running, and p is measured in miles. During the first seconds of her run, Catherine's acceleration is proportional. So let's stop right there and just think about what does the word is mean in math. Well, is, if something is equal to this, it's is the equal sign. And then when we see the word proportional, they're actually referring to directly proportional. And that's the part you got to be really careful. Is if they don't put the word directly in there, it's assumed that it's directly proportional. So I'm thinking it's going to be something like y equals k times x, where k is that constant. But what is it proportional to? Acceleration is proportional to the cubed root of the time since she started running. Write the differential equation that describes this relationship. So write a differential equation. Well, that was the rate, the change in this case, the change in position over the change in time. However, we have acceleration. So I want to take this statement, acceleration is proportional to the cube root of time, and I just want to write the differential equation, and they tell me k is a positive constant. So what do we need to know? We know that position is p of t. That's what they tell us in the start. We know that if I took the velocity of position, so I could write this as the change in p over the change in t. So that's the derivative of position gives me velocity, and then the derivative of velocity is acceleration. So that's the second derivative. And hopefully that you guys remember that from trimester 1. But what are we going to do? We're going to take the acceleration, which can be written as the second derivative, so d squared over dt squared is, so the is the equal sign, proportional. So when I see that word proportional, I'm thinking there's a constant k, and then it's proportional to the cube root of the time. So that just means we're going to multiply by, not cube root, cube root. Cube root of time. And that's all this problem wanted you to do, was set up the differential equation. Now, I'll throw this disclaimer out here. This type of question could potentially be one multiple choice problem on the AP test, and that's it. So if you get it, awesome. Most likely it's going to be something where they will give you options. You just have to kind of eliminate and look at which one is the best setup. So that's why I'm showing it to you today. I apologize for the small print. I don't know if you guys can see this. It appeared much better on my computer at home, and unfortunately I can't make it bigger right now. So let me just read it, and I'll show you what we mean by this. Those of you at home might be able to see it better. But notice it's a multiple choice, and they have all the options for what we have to do and set up. So your job is just read through something like this, and then pick the correct answer based off of what we know about what it's describing. So I'll read it to you. A scientist is studying relationships of two quantities, S and T, in an experiment. The scientist finds that under certain conditions, as the quantity S increases, the quantity T decreases. After taking measurements, the scientist determines that the rate of change, so right there, rate of change, I hope that screams derivative to you. When you see that, that's derivative. While looking at this, it's the rate of change of the quantity S. So I'm thinking right away, it's not regular S, it's the change in S over the change in time. So the bottom one, if you can see it, is dTdS. So that automatically eliminates the first two options, or the option A and D. Because we're looking at the change in S over the change in time. Well then, they're telling us how it relates. So, with the respect of time, and that's where ds, dt, you can't really see it, that's what this first statement tells you, right here. Okay? And then it says is, so that's our equal sign. And then we're using the word inversely proportional to the natural log of t. So inversely proportional is divide. K divided by, and then it's the natural log of t. And the only option is option C. So this is a small learning target in the big scope of things. I wanted to spend 10 minutes on it, show you what it is. My students last year, we've been doing this all third trimester. They got really used to it, and they were pretty comfortable with it. Guess what the answer is? I thought I had it blocked up there. But take a look at this one. This is about as hard as it gets. And I think you guys might be able to see this one a little bit better. And again, you shouldn't be writing any of this down. It's just getting exposure to it. So a rumor spreads amongst a population of n people. So n is the total amount of people we have. And it's a rate proportional. So there's that proportional. So I'm thinking direct proportion. So now, notice it says the rate. So I'm thinking d, and if you look at your answer choices, it is definitely dp dt. But it's proportional to the product, so product means multiply, of the number of people who have heard the rumor So we're going to multiply the number of people who heard the rumor and the number of people who have not heard the rumor. So that's what we're going to be multiplying. And then when we read later on, it tells me what those values represent. So when I think of proportional, that's k times something. So proportional is multiply. And what do we have? We've got the number of people who have heard the rumor. Well, if P denotes the number of people who have heard the rumor, we're going to multiply that, and we're going to multiply by the number of people who have not heard the rumor. So that's the hard part. How do we know who has not heard the rumor? Well, if P is the number of people who heard the rumor, N is the total number of people overall. If I take the total amount of people and subtract who have heard it, then this will be the people who have not heard the rumor. And that's all this is. You can look and see it was the option D that we had said. So that's just one small example. It could be a really quick point for you. And the big reason why I showed you this problem, that term, the rate proportional, will be the multiply. So, all right. This is what we do want to write down. So I'll give you a second. Go ahead and write the title. Good news is you're going to actually see today is a review of what we've done part of trimester 1 and part of trimester 2. Aaron, do you need paper? No? Yeah? Oh, okay. I got one here. So, hopefully, you see this title and you think, differential equations. We've done differential equations. That was most of what we did in Unit 5 and Unit 6, as we dealt with differential equations. So we got to talk about a couple things. Don't write the rest of the information on this slide. Just write the title. So we're going to just do a quick overview. What do we mean by the word ordinary? I think they just throw this word ordinary in there. An ordinary differential equation is an equation that involves an independent variable and a dependent variable, usually x and y, and then we can write that as a derivative, dy dx. So that stands for our derivative, but we have different notations. And that's what I'm going to show you here. Again, don't write these, but remember y prime? That's the same as dy dx. And then we can have x's and y's mixed together, and that's what we're going to be exploring over the next couple of days. But we don't have to have y. We could have p prime, we could have y prime, or I could have a second derivative mixed in with the first derivative, like the last equation here. Y double prime plus y prime equals some value. Now the reason why I show you this is we have a different way to just talk about the order. And I think it's pretty quick, so you don't have to write this. But we have something that is called the first order derivatives. All that means is it has the first derivative as the highest derivative in the equation. So if I look at these first three equations, they all have the first derivative involved in them. But what if I look at a second order derivative? Well, the last equation that we have written has the highest derivative in it is a second derivative, so that would be called a second order derivative. You don't really need to have a strong connection to that. I just want to make you aware of it. And then the parts that we should be really familiar with is how do we solve differential equations? Well, if y equals f of x is a solution to a differential equation, then y and its derivative are substituted into the equation, and the equation is written for all values. Well, the way we looked at it is, remember when we did that general solution? We solved the differential equation, and our answer had a plus c in it. That plus c represented a family of functions or different representations for an equation. The c was just a vertical shift up and down, which doesn't change the derivative, but it changed the actual location. But then we had the actual real solutions, which were called particular solutions. And that was when, what if I had this answer, y equals 3e to the x plus c. But then I told you, you know what? X is equal to 2, or 0, and y is equal to 2. What do? We plug them in to the spot for x and y, and then we solve. We simplify, and we find the c value, and then we take the c value and we plug it in for whatever c is, and now I have my particular solution right here. So instead of a plus c, now this is a specific solution that goes through the given point 2, 0. So hopefully we're still doing all of that. The only difference is it's going to get a little more challenging now. Okay? And here's what we mean. I do want you to write this one. This is a very common problem for us to look at in terms of AP level. And I would guess this is most likely a multiple choice type of question. But it says verify that y equals 2 e to the 2x plus 3e to the negative x is a solution to this differential equation. So what I'm thinking when I read this is I see the word differential equation. Why is this a differential equation? Because it has derivatives in it. So it's telling me that I got to prove that this y will satisfy this expression, which means I'm taking the second derivative, I'm going to subtract the first derivative, and then I'm going to subtract 2 times the original function. And all of that will equal 0. If I have to verify that, then I have to show that, or I have to prove that. So how do we do that? Well, what do I need? I need 3 pieces. I need the yellow, green, and the blue, but they give me the blue already. Right? They're telling me that y equals 2x plus 3e to the negative x. And just by knowing that that is the original function, I can use the chain rule to find the first derivative. And once I know that, then I can find the second derivative. So you can see why we're doing a problem like this. It's reviewing chain rule. It's reviewing all the stuff from trimester 1. So hopefully you see that. But we're going to go ahead and take the derivative of the original function here. And when I take the derivative of e, I get itself, e to the 2x, but there's a chain rule here. Right? Then I have to take the derivative of the 2x, and I would put a 2, and instead of putting it behind, we're going to put the 2 out in front. So remember, that red 2 is a chain rule. And then we're going to do the same thing with the next piece. I've got 3e to the negative x, and the derivative of the top part here is negative 1. But instead of putting a negative 1 like this, why don't we just make this 3 negative? So that's what, that's what I would do. Instead of putting the negative 1 with the chain rule, I'm multiplying that by the 3. So hopefully you can see we had to use the chain rule for each piece. And now I know the first derivative. So what I'd like you guys to do is, knowing that you're going to have to do the chain rule again, go ahead and write the second derivative right now.
did you keep the 2x as a negative x?
Oh, when we have a function like e to the x, its derivative is just e to the x. And if there's a number up here, so like let's say this is e to the 7x, then the derivative of y would be the exact same thing. So that's the derivative rule of e to the x, but then we'd have to multiply this by 7 because the derivative of whatever's up here, you times by that using the chain rule. Okay, so I'm going to do the derivative here. The derivative of 2e to the 2x is going to be 2e to the 2x and then times 2, but instead of writing a 2 here and then a 2 here, I'm going to just say, well, the 2 times 2 would be a 4 out in front. And then the derivative of 3e to the negative x is going to have another negative come down, but that negative is going to make the blue negative turn into a positive. So there's my second derivative. And now you notice I have all the pieces that I was looking for to satisfy this differential equation. So our job now is to plug all those in and be very conscious of that negative and show that when I do this, I'll get 0. So let's see. I'm going to use red for the second derivative. And then we're going to subtract. Now notice how I'm putting parentheses here. I'm going to subtract the first derivative, so I'll use green for that. And then I'm going to subtract 2 times the original function, and that will equal 0. So all that is a substitution, and then you just got to make sure you're very careful with distributing the negative, because that's, to be honest, that's probably the biggest mistake. It's not calculus that students make the mistake on. It is the algebra. So once you distribute the negatives, then you can kind of see some things are going to cancel out. And we're talking about like terms here. So I'm going to look at the ones that have the e to the 2x. I've got 4, negative 2, and negative 2. Well, those are going to add up to 0. So really, you can cross those out. And look at what's left over then. I've got 3e to the negative x plus 3e to the negative x. So that's 6e to the negative x minus 6e to the negative x. Those are going to add up to 0. And I don't have to show everything canceling out. But I showed that the left side is equal to the right side. That makes me happy. It works out. Okay. So that's one type of dealing with differential equations. We technically could have done this problem, and probably did, during first trimester. I don't want you to write this one. I just want to show it to you quick, because this is another problem that you've seen. It's just the notation is different. And it's one of those problems that says, okay, here's my original function, right here. We want you to prove or verify that its derivative is right here. So you want to show that dy dx is equal to that. And hopefully you remember doing a problem like this on a test. What do we have? I've got the original function. take the derivative to show that dy dx is equal to that. Well, the reason why we do this problem is, if you remember, this is called implicit differentiation. So we're going to take the derivative of each piece, and you'll hopefully have some flashbacks here. If I take the derivative of the first x squared, remember how we put dx dx? We're taking the derivative with respect to x. But then we run into this problem right here. That's a product rule. Right? We have x times y. Actually, it's x to the third times y. So I have to use the product rule here. And I'm hoping we're really good at this, so I'm not going to show a lot of work, but I'm going to take the derivative of the first, which will be negative x, 3x squared, dx dx, times the original y, plus the original first part, which was negative x to the third, times the derivative of y, which is dy dx. So all of that came from the derivative of those two pieces, the product rule. And then the last part, what's the derivative of 3 plus y to the fourth? Or I should say 3y to the fourth. That's 12y to the third dy dx. And then the derivative of the plus c is 0. And then remember, dx's over dx's reduce out. So those are going to move over to the other side. So I don't have a ton of room, but I'm going to actually take the 2x and subtract it over. I'm going to take this negative 3x squared times y, and we're going to add it over to the other side. And then what's left over here is the two items that didn't move over to the right side have a dy dx in them. And that's where we factor that out. So what's left over? I've got a negative x to the third and a 12y to the third. So we factored out the dy dx, and that's our goal, right? Is to get dy dx by itself. So then the next thing is we'll just divide to get dy dx by itself. And my goal is to make it look exactly like what I wanted to show. So notice how I had this negative 2x written first, but the answer had it written second. I'm just going to write that as 3x squared times y, and then we'll do minus 2x. So I just flip the order of these two, which is fine. And I'm going to divide, and I'm going to flip the order of those two just to make it look exactly like what I want it to look like. And we're done. So hopefully you remember doing that. Just kind of a quick review here. And we're going to skip that one. And I do want you to write this one down. So this is the big part of, we will be doing a lot of this unit. We're in unit 7. It's a shorter unit. The nice thing is it ties back into these differential equations. So remember, the differential equations are anything that has a derivative in it. So there's my dy dx. That's how I know it's a differential equation. But this time they say find the general and the particular solution. So when I see find the general solution, I have to have a plus c in it. When I see find the particular solution, I have to use the given point 6, 0. Now, what do we do? Well, some people like to think general solution is plus c, particular solution is use the point 6, 0, which is the x value. So, what's the first thing that we do? Well, we can't just take this in the form that it is in because this has a dy dx. I need to take this dx and move it over to the other side. So it's set up as an integral problem. That's how we solve differential equations, is we take the integral on each side. Well, that's pretty friendly because on the left side, we've got 1 dy dx. So whose derivative gives me 1? That's just y. But then over on the right-hand side, we've got a more complicated integral, which, if we have more complicated integrals, then we do use substitution, which is what we just covered in the last unit. So hopefully, you're very comfortable with this. I'm going to let the middle part, 4x plus 1, is going to be u. So then to find du, we take the derivative of that. But I don't have an extra 4 in my problem. You could get creative and get rid of that too, but I would just say, you know what? Move that 4 over. Now I can set up my new integral. So what happens to the 2 original? Well, the 2 is just a multiplier, so that's going to float outside the radical. I still have the square root, but now it's going to be the square root of u. And then instead of writing the dx, we're going to replace dx with 1/4 du. And that 1/4 will float to the outside. And that made the integral easier for us to deal with. So I can simplify 2 times 1/4 is 1/2. I still have the integral of u, but it's a square root, and we don't like that square root. So we're going to actually change it so it looks better. So I'll rewrite the square root of u as u to the 1/2, and now it's time to integrate, which is undoing the power rule by adding 1. So this becomes u to the 3/2. If I put a 3/2 up top, I got to put a 3/2 in front. The 1/2 multiplier is going to stay. And then we have plus c. We'll notice that the 2's are going to cancel out. 2 on top, 2 on bottom, so I'm left with 1/3, 3/2, u to the 3/2, but instead of u, now where we replace it. Alright, so there's my general solution. Right? It's general because we put the plus c at the end. So that's the green part of the directions. But we're not done, because it says find a particular solution. Well, you did all this work. Now all you do is use the given point, 6, 0, and find the c value. Like I said, we've done this already, so we're not going to spend a ton of time. So we plugged in 0 for y, 6 is x, and then do some quick simplifying. I know that 4 times 6 is 24 plus 1 is 25. And this would be a perfect no calculator free response question where you have to show all this work. So then they're expecting, do you know how to do 25 to the 3/2 power? Well, hopefully hopefully you're thinking, instead of 25 to the 3/2 power, you're going to write it as the square root of 25 to the 3rd power. Because we know what the square root of 25 is. And then I know that 5 to the 3rd power is 125. So they assume that you can do all that green stuff in your head. So then I just have to make sure that I get C equal to whatever it's going to be equal. In this case, C is going to be equal to negative 125 thirds. And then you do have to be very conscious of what you're doing. We're not done. Right? I can't just stop here, and it would be really unfortunate if you did. Because we need the exact solution, or the particular solution, which is taking the general solution that we just found and adding the C value to it. So make sure you finish exactly. There's your particular solution. Some of this stuff we went through pretty quick. But hopefully it's just building your confidence up with thinking, you know what, we've already done this. Okay. I think I'm going to hold off on this one. I got one last problem. This is up to you if you want to write it or not. But it's a perfect connection with particle motion. So if you look at it, what does it tell us? Well, it says a particle moves along the x-axis with a velocity. So we have the velocity function, which is 1 over the square root of t. They tell us that at the time and the position, at time 1, the position is 4, find the acceleration and find the position. So we actually have to take what we know and work in opposite directions. What do we know? I know that the velocity is equal to 1 over the square root of t. I don't like the way that that's written. I'm going to rewrite this as t to the negative 1/2. Okay. So that's velocity. Cool. Nothing crazy. What do I do to velocity? Find acceleration. Well, from trimester 1, if we know velocity, we take the derivative, and that will give me the acceleration. So acceleration is just the derivative. This is just a quick power rule. The negative 1/2 comes down, and then I take 1 away up top. It'll give me negative 3/2. So all we did was take the derivative. Notice how the initial point that was given, we didn't have to use. Don't think of that as trimester 1 stuff. But the newer material is if I have acceleration, I have to undo the derivative to get to position. So now we're going to do the integral or work with the derivative. So remember, position is x of t. Sometimes they write it that way. So that just means I have to take the antiderivative of the given velocity function. So when when we do integrals, we add 1 versus subtract 1. I'm going to add 1 up top. Nope, that's not right. If I get a 1/2 up top, then I have to compensate for that and put a 2 out in front. And there's my position equation. But we're not done, right? That has a plus c in it. That's a general solution. I want specific pieces because I know that they gave me a specific point. You have to be super careful with this. T is 1, and x of 1 is 4. So they try to trick you by saying x is 4, and a lot of students think that's the input, and that's not the case. We're going to plug a 4 in for the output, and we're going to plug a 1 into the input. And now I can find c pretty quickly. You don't have to show a ton of work here, because I know 1 to the 1/2 power is 1. That's 2, and when I subtract 2, I get c equals 2. And I'm just going to go right back to where that c first appeared. And there is the exact position equation. So you will definitely see some form of question like this. This is one of the ultimate questions, right? We'll give you the velocity. You have to apply trimester 1 knowledge to take a derivative and find the acceleration. You have to apply trimester 2 knowledge to undo derivative to get the position, which is the integral. So it's a problem that these are great calculus problems because it requires knowledge from all different pieces of the year. Okay, so most of what we're doing today is going to be going from like a velocity to a position, but it might not be context-based. It might just be, here's a differential equation, go ahead and solve it. So what we have as homework tonight is, it's in our textbook, and I do want to show you this just to make sure that it's up there. When you go to Schoology, I hope you are all really comfortable with just, if I go to Schoology, we've got the homework answers here. So in Chapter 7, here's all the answers to tonight's homework. I show you this because I want you to check your work as you go. And I try to show a lot of work to help you out, so it's not just like in the textbook. Sometimes they just skip a ton of steps and assume you can make it work. So anyways, all the answers are available. Please use them to help guide you and check your answers. Down here, this is the link I want to show you quick. If you click on this link, you do have access to the online textbook. We didn't use it a lot because you do have to set some things up. So if you're interested, you can click on this first link here, and then you will have to type in some things. It's not going to give you exactly what I see here, but you have to search, and you'll have to like type in North St. Paul, Maplewood, Oakdale, and I think once that comes up, that'll bring you to our specific district. And then you have to create an account, and once you create the account, then you can access the e-textbook on the side. If you need help or you really want to use the online textbook, let me know. Stop into my office hours and I can help you out. Okay? So anyways, that's how you can access the textbook and make use of it if you need it. So what about my office hours? How is that going to work? So students, you guys in Tartan today, you're going to come back in class at 12:55 to 1:30. And that is going to be our time to just work. Once we get into review, we're going to be using that time to do AP review questions in class. But for the first week, for sure, we're just going to do homework help. So you'll get started on this homework today, and I'll be bouncing around. Students that are on Zoom right now, you are encouraged to attend. If you have any questions or need any help, stop in from 12:55 to 1:30, and I'll go through homework problems. I can help you get set up with the online textbook, whatever you need. All right? So, I got to reach out to one person on Zoom, and then after that, we are officially done. So, my Zoom people, don't go anywhere until I let you know that I've contacted the person I need to contact. Okay, so if you check the chat, and please respond to it if you got one. If you didn't get one, you are free to leave Zoom. Have a great day.